I would like to, I'm happy to present Anne-Marie Kermarrec, who is, well, now she's the CEO of a company, Midiego, which is specializing in recommender systems. I'm gonna talk about her experience on using machine learning, distributed machine learning for recommendation systems. But originally, she's coming from academical research from INRIA Institute in France, and since recently she joined the industry to apply her experience in distributed computing to the practical stuff. Okay.
Thank you, Petr. So I wish it would be industry already. So for now, it's a very small startup that I'm running. So basically, I started to work on. So I'm mostly, as a researcher, my area of expertise was distributed systems, and I did a lot of things in peer-to-peer systems. And then more recently, I got into recommenders, and basically, I worked on algorithms, recommender algorithms, but more on the system side, saying, how can you implement this efficiently? And then I worked at the time in academia on the peer-to-peer recommenders, which is basically going to be what I'm going to talk about today. And now in my company, we are building such recommenders for our clients. But obviously, the peer-to-peer system, peer-to-peer paradigm is a great paradigm with respect to scalability and efficiency. Now, when it comes to a business model, it's not such a an easy thing. So we're doing more distributed system than peer-to-peer systems. But anyway, so I've been working, I would say, this is really the goal today, is to basically give you the basic. So it's going to be very different from what you heard, yesterday and this morning. So it's my goal here is to just give you a sort of a crash course on one kind of recommenders, and also give you a hint of how you can build this in a fully distributed manner. So I have an hour and a half to do this, so I hope it's going to be fine. So please do not hesitate to actually ask questions whenever you want or you need clarification. So okay, so why do we need recommenders? So this is very quickly. We already today face a huge volume of data, and you have users which are more and more demanding, more and more experts in different things. And if you think about it, there is a tiny space, so to time and space window to actually retain them. So this is more of my corporate kind of motivation, but the goal here is to make sure that you provide the right content to the right people at the right time. Now, so there are examples of recommendation all over the place. Okay, probably the most well-known is the one from Amazon. So Amazon was the first to actually introduce recommenders in their system, and what they claim is that there has been a 30% increase of their sales when they put this. So basically what they're doing in Amazon is that they usually call this, people who actually like this or bought this already, also bought this kind of thing. So this is exactly based on some of the recommendation algorithm that I'm going to talk about, which is collaborative filtering. Now, another kind of recommender, which is also very important, is Netflix. In Netflix, basically, the entire interface is a recommendation system. So I don't know to what extent you are using Netflix, but if you go and try to navigate into Netflix, this is a nightmare, okay? And actually, the entire interface is about them providing you with whatever you want to watch, okay? And so in a sense, the recommendation system there is extremely important and is really the core of the interface. And it's, according to them, generate 1 billion revenue also. Well, now you can think also as a Google search results as a recommendation system. And in a way, this is what it is. It just rank, the different research depending on what you've been doing in the past, what some other users who are doing the same thing as you did do. So that can be seen also as a recommendation. So this is another kind, which is a different one in the sense that it's more like it's not, it's implemented more as opinion aggregator. So basically, when you have this, you get on TripAdvisor and these kind of things, you get whatever is the most popular. But this can be seen also as a recommender. So any other example of a recommendation system that you use probably daily? No? Okay, which is about the same example as Google. Any other thing? Well, another example that I didn't give, where it's all about a recommendation system. Maybe, yes, that's a good example. Well, actually, you can see Facebook as also, so you're not using Facebook, right? So anyway, so this is really a recommendation system, okay? And it's kind of a dangerous one in a sense, because what it says is that it basically, again, as Netflix, the entire feed is actually personalized, okay? And if you're aware of this, then that's fine, because you know that you don't get everything. Now, from time to time, you still, especially people who are not computer scientists, they just don't even know. And so they think that some of their friends are just quiet, whereas just because they do not generate activity, that their news do not appear on your feed. So this can be seen as a recommendation system. Anyway, so you have plenty of recommendation system all over the place, and they're used in addition to also to the systems that are used to discover friends in social networks or, Facebook, LinkedIn, whatever. Although I just noticed that LinkedIn here is sort of blocked. So I heard that it was because they do not translate in Russian well enough or enough. But anyway, so you can actually discover professional, clients, whatever. And it's basically all over the place. So if you think about this, the goal here is to provide users with what they want to do. Okay. Now we can discuss in length about the ethical kind of things, but that's not what we're going to do today. So today, what I'm going to talk about is basically one kind of recommenders, which is collaborative filtering, which is used in many of these different places. And then I will tell you how we can build a peer-to-peer search recommender system. Okay. So I would say that concurrent distributed parties in that part, and this is more about one kind of application. Okay, so basically the recommenders are based on some other opinions. Okay, so this can be your own, as a user, your own opinions. Okay, and that's pretty much what the basics recommender could do, like just based on your recent history. You can have also a set of experts. So this is also used in some things. You can take everybody, like in kind of TripAdvisor or Zagat or these kind of things, where everybody's opinion is used. And then you can also take a look at people who actually think or do things like you. Okay, with some precaution in that case, because you probably heard about this bubble of interest that we can have, especially on Facebook. This has been very popular, and then you need to take care of this kind of thing. So basically, the first question you have to ask when you build a recommender system is, what is information that you want to use? Now, with respect to output, when I'm going to use recommendation here as a very broad term, okay? But this can really come as recommendation in the form of a scoring of some items, okay? Or it can be just prediction of what you want to do, or what is the next action, or what you want to buy. It can also just be a filtering kind of information. So you have many ways of displaying the output. So for instance, in a social network, it can just be a set of friends that you want to get, or for instance, on the Facebook feed, it's really a ranked list of items and so on and so forth. Now, in terms of input, so that's basically the output of the recommenders. In terms of input, basically you have two ways of catching some information about users. The first one is basically the explicit. So this is when, for instance, on Netflix, whenever user actually put a number of stars on the movie, or this can be comments, which can be analyzed in different websites. That can also be the like or not like or share or no share kind of thing, okay? Now, the implicit one is the one that you basically gather without the users being necessarily active, okay? I mean active in the sense of the recommendation input. It just means that, for instance, you're recording the navigation history or the action, like you put this in the basket and not, but these are actions in the sense, explicit action for a website, but not from the recommendation system. Okay, this is different of putting stars. So this is the two things you can do. Now, in terms of recommendation system, you can go into basically non-personalized one, which are still recommenders. You can do content-based, and then you can go into collaborative filtering. So I'm talking here unsupervised kind of method in this case, okay? So I'm just going to go very quickly through the two first kind, and then the focus of today is going to be that one, okay? So it doesn't mean that the other ones are not used, but that's what I'm going to talk about. So basically, in terms of non-personalized, the non-personalized recommenders that you have out there are the ones that actually basically gather everyone's information. And still those are used quite a lot, okay? If you think about restaurants, those are still, or hotels or stuff like this, those are still the ones that are the best, the most popular. So it's basically trying to get out the most popular news, most popular items. That's also used quite a lot in online media, okay? And this is not personalized, but this has some merit, but at the same time, you have no idea of the exact profile of a user, and then, especially for users who have a very different taste, it might be very difficult to catch, okay? So I'm not going to stay for long here. So now consider this model that we're going to use for the rest of this talk. So basically, you have a set of users, so we consider a set of users, we consider a set of items, and there are some ratings. So that can take the form of scores, like, action, whatever, okay? But it means that basically when you relate a user to an item, you can relate them through an action, okay, with potentially some weight. So you potentially have, depending on the model, some user attributes, and you potentially have also some item attributes. Now, before going into collaborative filtering, I'm just going to tell you how content-based filtering could work, okay? So basically, in these kind of things, you are trying to build up a model for every user, okay? And so you have a set of characteristics which are applied to items, and then you are going to build a user taste vector, okay, which is going to take into account the characteristics of the items, all right? So let's take an example here. So if you have this example that Alice loved that movie, okay, so maybe she liked it or shared it or whatever, but you have this rating here. What you can say that you can have a look at the item characteristics, okay, which is basically something which is explicit, and you can say, well, for instance, this is, so you have a set of attributes that you would put in a user taste, okay, say you have these two attributes, well, three attributes, so maybe Star Wars is going to be, checked with sci-fi, but then it's not with Leonardo DiCaprio, as far as I know. And then it's not considered as an adventure. And this actually is, and then so in the taste vector of Alice, you would say sci-fi, yes, okay, with a given score, but then with Leonardo DiCaprio, no, and then adventure, no. Now you can already see what can be a problem here is that for some people, and actually I saw this example to some of my students, and they would disagree, okay? Because they would think that this is kind of a characteristic of the movie. So you already face here the fact that with this kind of things, every time you have some explicit choice in the attributes or in the way you put them, then you might have some difficulty to actually reach an agreement. So basically the example here is that whenever you get a new movie to recommend, say The Revenant, then you can tell to what extent that matches the taste of Alice, okay? And then you get another kind of characteristics, and the revenant, if I remember correctly, this time is with Leonardo DiCaprio. And then in that case, you can see that it doesn't match, or it doesn't match Alice, but it does match someone else. So this is the way you do it, okay? So that means inspecting the content and dealing with some metadata. Yeah? So in terms of, models, this is how we use it. So this just to show you that whenever you go into content, then you might have some problems into expliciting these kind of things. So now I'm going to talk about collaborative filtering. So who knows what collaborative filtering is? Okay, so it's, so sorry guys. You're gonna hear this again, but you're not so many. Okay, so basically the guy of, the goal of collaborative filtering is not only to use your own history, okay, or your own data, but also to use the data of the others. And somehow what is, the sort of motto of this algorithms is, using the wisdom of the crowd. So that means that you are going to leverage every information you can have. So you have two different ways of doing this, okay? So at the heart of this is to try to find some resemblances between stuff, okay? So it can be between users, or it can be between items. At the end of the day, it's always between users, right? Because these are the users that you want to satisfy. But you can go either through the users themselves or through the items that they are consuming or watching or whatever, okay? So in the case of user, what you need to do is basically, the goal here is to find the people that basically look like you, okay? Whatever that means, we'll get back to this. And then use the opinion of the others. So say, I'm very much like you guys on the first row, then whatever you do might be a very good thing for me, okay? So the basic assumption behind collaborative filtering is the fact that if you have done something similar to a given user at some point, then you will, again, in the future, you have a high probability of doing, again, something which is very similar. Now, you can do this the same as item, okay? You can say, well, two items are very close if some users, same set of users, have actually watched them or consumed them or whatever, okay? So these are two different ways of finding similarity between users, either through the set of items indirectly that they have shared, or directly with their profile, okay? Today I'm gonna talk about this, and you'll see why, because at the end I'm going to present the fully distributed systems, but just bear in mind that you can have the exact same thing with item, and you can think about the difference it makes with respect to system at the end. Now, there is another very well-known way of building up collaborative filtering, is everything which is related to reducing the dimensions through matrix factorization, for instance, okay? I am not going into this today, okay? But this is a very common thing that is used. So typically, this is probably what Amazon and Netflix are doing. Now, one of the things that you have to see is that when you go for matrix factorization, basically, I'm just saying one word because I'm not going into this so after that, is that you start from very big matrices of tastes, which we're going to see, and then you just sort of reduce this by basically reducing the dimension to a few features, okay? Now you have to do this, and then once you have this, you can compute very quickly the scores for every new item that you want, and compute very quickly the recommendation. But then this needs this computation. So basically, whenever you have to do things on the fly and in real time, then it means that you have to, when you have a very dynamic set of data, it means that you have to go through this path again. And this can take sort of a long time. Okay, so what is the model that we're considering? So basically what we can imagine now is that we have a set of users, okay? We have a set of items, and basically the users, they put either some score or just the fact that they watched something or liked something or whatever, so that can be binary ratings or not binary, it doesn't matter. And the goal of a recommendation system basically is to come up with some recommendation, okay? So one way to do it is to come up with to fill up the matrix so that everything is filled up, okay? For instance. So basically what you want to do is that you want to assign a score of you for user U to the item I, okay? And you want to do this depending on the rest of the data that you have. So just bear in mind that usually it's a very sparse set of data, and that you have only a few parts of the item that are there, okay? So this is what we want to do. Okay, so this I talked about. So okay, two things that sort of qualifies the collaborative filtering approaches as opposed to some of the part that we talked about earlier, is that you basically are able to extract some information that are not there. So for instance, what you do with this prediction, that you are able to decide that I'm going to like item X and Y and so on, not just because of my history, but because the people who look like me did this kind of things. Now, the other thing which is interesting and has to be opposed to content-based approaches is that this is completely agnostic to the content, okay? You're not inspecting the content, okay? You're just looking at whether people are alike, okay? To some extent, you don't even care why they are alike. What you care about is that they look alike. So this is one of the things that make them attractive for some application. So basically, in such a system, each user has a profile. So basically here the profile would be the set, so it's a vector of items, okay? And then you put either a score or, in that case, that's an example of a binary. So you want to know this one I mean, she didn't like it, for instance. Now that one she liked, that one she didn't. And then you want to know what is her opinion about those ones, okay? And what to do this, you're going to see whether she looks like some other users, and then to infer what you would think of these kind of things, okay? So basically, the type of collaborative filtering techniques that we're going to use today, our goal is to find the K closest neighbor, okay, according to some similarity. And then once you have this, well, that's easy to actually leverage this information to basically do some prediction. Okay? So basically so there are two parts in this kind of recommendation algorithm. The first one is to know who is close to who. Okay? And the second one is, okay, what do we do with this information? Okay? So we're now going to go through these two steps. And once we are clear on this, we are going to see how we can do this in a completely decentralized manner. Okay? All right. So far so good. That was very sort of high level at this point, so I would expect it's still okay. So in a user collaborative filtering, again, just remember that I put user everywhere. You can reverse this and see this as an item as well. So you would try to get some predictions. So you have a set of users, and you would have a rating, for instance, of AI would be the rating of a user A for an item I. So what would be, so let's just start slowly. If you were to implement a non-personalized version, what you would do? What would be the natural thing to do? Yes, so how? Exactly. So basically I guess, if you were going for, I mean, that was a question, or that was a... Yeah, okay. So you're right. A non-personalized version, right, would actually be to do this, to assume that you are going to take the opinion of everybody for this item, and this is typically the prediction for user A for an item I would be whatever you get on that item. Okay, and you just average this. So this is typically what you get in those opinion aggregator, okay, kind of thing. All right. So basically, so what's wrong with that? Exactly. So basically, the issue with this is that it's non-personalized in the sense that everybody is involved in this computation, whereas some of the users might not be relevant actually for this set of users. So, how would we do this? Okay, so let's go slowly because it's right after lunch. So now imagine that you have a way to reflect how close two people are, okay? So what the simplest, so you have this, take this as an assumption. Then we'll see how we... Exactly, okay? So this is exactly what you do. You consider that you have, a metric here, which is a weight that basically would reflect the agreement between two users, A and U. And then what you do is that you just, use the rating of everybody, but you sort of normalize this through this weight of two users, and this is how you come up with the score of a given item. Okay. Now, what can be wrong with this if you do this just like this? Yeah. But then somehow what you can argue here is that this is expressed in this weight. Okay, say I'm closer to Michel than to you, then maybe my weight here would be 0.8 with Michel and 0.6 with you. So this is accounting for in that sense. So what is the... So the problem I'm relating here is exactly the same as a professor or a teacher who can grade... Okay, say you guys are a class, and then I'm gonna grade this part, and Rashid is gonna grade this part. So what can happen? Exactly. The thing is that I might just use like part of the scale, okay, around the average, and he might use the entire scale. So basically, this is one of the things. So this is just one example of all the tweak. I'm not going into all of them, okay? But all the tweak that you can have actually in such an algorithm. Okay, so basically the way it's done usually is that you take the average. The way you can deal with this is that you take the average value of a given user. So say you have a user who actually use all the scale from 1 to 5 for a movie, and the other one is just binary, like he used 2 or 3, 2 when he doesn't like, and 3 when he loves it. Okay, so then what you can do is that you can basically normalize with this the average rating, and that provides you with a better one. Okay. Okay, anyway, so the two similarity, I'm not going into this, okay? Okay, you will find as many similarity measures as you find, potential author in the conferences that are associated. I mean, there are plenty of different tweaks and things that you can do. Now, these are the most common ones that are used, and again, my goal here is to tell you how it's used and how we can implement them efficiently and in distributed way, not to come up with a new metric. So the Pearson correlation is actually the one that is using this normalization, using the average. And actually, it's a very common one. Another one which is common is something which is known as a cosine similarity measure, where when it's done on the normalized rating vectors, then it's equivalent to the Pearson correlation. Basically, here what I find nice with this is that it's a very intuitive way. You can imagine that you have vectors, which are the dimension of the vectors are actually the size of the item set. Okay, and basically the similarity between two users is the angle that is provided with these two vectors. Okay, and this is a very intuitive way of seeing that some users are close. now, so now we know basically that, so say we're taking this one, we know that whenever you have two users, you can come up with a similarity measure between those two, okay? And this is based on their profile of items. Now, what can be actually, okay, so this is how it works, okay? Now say that you want to implement this, okay? You're a company like mine, and you want to implement this. So how would you do this? Because, I mean, what can be the issues? Let's put it that way. Yes. So sparsity, I mean, that's for one user, yeah? Yeah? Yes. Exactly. So one of the main problems is actually the complexity, which is related to this algorithm. If you want to do it in a completely brute force manner, is that you have so many users that it's an issue. And actually, this is one of the differences between the user schemes and the item schemes, is that there are many more, on a standard application, there are many more users than there are items. Okay, so when it comes to computing this similarity, you would be better off in a way with respect to size with item because you have less items. But then of course, there are some solutions. So basically, the problem with implementing such algorithm, as we talked about them like this, is that if you have m users and items, basically the correlation already, I mean similarity, okay, between users is already at the order of n, the number of items. But if you really want to go into all the correlation, okay, then you would need, that would be the order of m square n in terms of complexity. And obviously, this is already something which is very high, but this is not something that you can afford to do very often. Now, that's only for computing basically who is close to whom, but then if you on top of this want to do the recommendation, then you have a lot of work to do. So what could we do about this to make it more practical? Okay, so you said a lot of things, but the one that, so basically what you're saying is that you need to reduce this. So what that means is that, okay, so there is one thing with sparsity, so that's okay, but then when it comes to actually the sparse, yeah, when it comes to actually doing some, peer-wise comparison, the sparsity is not just an issue because it goes very quickly, okay? But again, you can still have some compact data structure to do this. Now, the question really is that the main thing, okay, is to actually not compute the similarity with everybody else, okay? There is a high probability in a sparse network that you actually will, especially because it's sparse, there's only a few users that are actually relevant to you, okay? And those ones are the ones with whom you want to compute the similarity, okay? The rest is probably irrelevant, so that's one thing. So then you can go into more systemish kind of thing, but this is the one we are going to talk about for now. Now, the other thing that we'll talk about later is how to actually, if this is a very expansive task, I mean, as many tasks, that you want to, for which you want to improve efficiently, when it's a large thing, what you want to do is to distribute the load, okay? So that you can actually do things in parallel. So we'll come back to this. But really the main thing is to be able to select the right set of neighbors. And once you have done this, and not to compute similarity with everything, once you have done this, then you will be able to compute the recommendation. So basically, if we come up with what is a collaborative filtering, again, user-based collaborative filtering algorithm, this is pretty much what you do, okay? So basically, the first task is to select your neighbors. So in other words, that means this is where you need to compute the KN nearest neighbors. And KNN is a kind of algorithm that is used all over the place, okay? But you can use this. You've known about KNN, you know about KNN systems, right? So this is used in many different things, including, when you want to match some images in a large database, whatever. But this is also what we're using. So basically, we are going to use such algorithm to select the neighbors. Once you have the neighbors, you can compute the neighbors on which you are going to compute the similarity with. You are going to compute those similarities, potentially normalize them, and then come up with the closest ones. Once you have the closest ones, you can compute the prediction, okay? So you do this in a very large system with a lot of users, okay? And potentially sparse matrices. Okay. So again, as I said, when you select the neighbors you want to compare with, you are going to basically just going in terms of complexity. It's not something that you want to do, and then some are relevant. So there are a number of metrics that you can do. So one is that you can say, okay, so there are two things. Okay, here is more like when you select the neighbors with whom. From whom you are going to take the opinion to compute the recommendation, okay? So if you're taking all of them, not only it's going to be expensive, but in addition, they won't add anything, okay? Say this part of the world is just very far from me. Taking their opinion is just useless in my in predicting. So you can go with the threshold similarity, okay, and say I'm going to take the opinion of the user for which the similarity is over 0.5. But then you end up with a similar situation that maybe 0.5 for a given application is a good metric, but maybe it's a very bad one for another application, so you don't want to do this. You can take some random neighbors, okay, which is basically the same output as selecting everybody, but then on a very small portion, and then you extract some information. But actually what is done most of the time is to take the top K neighbors according to that similarity metric, okay? Now, hybrid approaches also exist. What that means is that basically you can take this, but also use a threshold similarity and all this kind of things. Yeah. Yes. So this is actually not a matter of similarities. This is a matter of how you display the recommendation and what a user is exposed to. So this is exactly what is going on Facebook. Okay. So basically, if you are exposed only to things that to things coming from people you are close to, you're going to get closer and closer. And yes, that's an issue, because then you're going to be further and further away from the people in South America, say, and then you will never encounter them, okay? And this is exactly what happened with the so-called bubble of interest on Facebook, and, there was all this discussion around the American election, that some people just, evolved in completely different spheres on the internet, and that never reconcile in a way. So I agree with you. But that's not a problem of the algorithm, or that's not a problem of the similarity. It's a problem of what you do with the output of the recommendation. So basically, my take is, if you personalize everything, yes, you are going to enter in these kind of things. So one way to avoid this, it is to do, for instance, probably what is done on Amazon, which is like you can have the things that people like you did, but you have also, say, the most popular things, and you have some other things. A very good way, as very often in computer science, to avoid these kind of things is to throw randomness. Okay, so basically in sort of personalized vision, you have also some randomness, then you might get exposed to these kind of things. Yeah, but I agree. But it's not a matter at this point of the recommendation, it's what you do with them. Okay, so again, this is on the practical side. What you do is that, because even though in theory, the more information you have about the users, the better you are, in theory, basically what matters is between 25 and 100 of those neighbors. So you put K at between 25 and 100, and that works fine for many applications, okay? So what that means is that out of in a very large scale system, okay, a few million, even a few billion, if you take, say, 100 with K, so for each user you identified the 100 which is the closest, then you end up most of the time with good results, okay? So that doesn't solve the problem of who you compute the similarity with for now, but that solves the issue of how many profile you're looking at when you want to compute the recommendation, okay? And yes, and then this is what is used in practice most of the time. Now, the thing is that there is a trade-off here between that can actually be an issue, and I'm facing this right now actually with this company. Is that if you have too few, okay, you will have very good neighbors in a way because you're very close to them, okay. But if they are not very active, you don't have a lot of things to extract from them, okay? So say you're very close to a set of friends, and this, going back to your problem, you're very close and closer and closer, but then you guys are doing only the same thing. So then, you know, whenever there would be one new item, then that would be a very high score with respect to precision in a way, but you will get only a few of them. So there is a trade-off here. On the other hand, if you select as neighbors a lot of different neighbors which are, you know, not as close, basically when you get some recommendation or some prediction, they might not be as good, but you will get more of them. So you get exposed to more things. And so there is a trade-off here that you can actually play with. So this is how many neighbors you want to consider for computing the recommendation. And usually the way you compute the recommendation is that, so you have two main ways of doing this. Either you average the score of your neighbors. Yeah. No, that's not the problem. I'm referring to the problem of users who have very close neighbors, in the sense that they are very similar to their, say you set K to 25, okay? And for each user you were able to identify 25 users who are very close, okay? But they are so close that there are not a lot of new additional information that you can find in their profile. Yes. Yes, exactly. So that's another problem. That's more of a cold start problem. Yeah. So there are several things, right? I mean, as a new user at the beginning, there's not much you can do. Okay. Now consider. Okay, we can come back on this, and there are some ways to deal with these kind of things, but. Now consider kind of a permanent regime kind of system where you have a number of users. They have seen, say, enough, whatever enough is for a given application, and they have a profile, okay? Then the parameters that you have to deal with are actually how many neighbors. So what is the similarity metric that you're going to use? How many neighbors are you going to use? And what you do with those neighbors. So basically you use either you average the score of your neighbors to find the new prediction, or you do some weighted average, which is usually what is used. And then the issue I was referring to is that out of this, say, 25 neighbors, somehow if they do not cover enough the space of items, then you can be stuck. Okay, in the sense that you do not have enough recommendation to provide to your users. You can always select more, yes. So if you select more, so then there are two issues. Either you select more because you have them, okay, and that's fine, and then you will basically increase your what is called coverage. I'll come back to this, but you will decrease the precision. So there's a trade-off, as many different situations when it comes to practical systems. So when in theory there is no trade-off, okay, it's possible or it's impossible. That's good. Now, when you come to implementing things, there's always a trade-off, okay? Because in terms of quality or coverage or whatever, or complexity, or so you have to make some choices, and that's what makes system and application sometimes difficult to run. Okay, so to take away of this part, okay, basically there are plenty of approaches to do recommendation. One very useful one that works well is a user collaborative filtering, which basically comes down to picking up a similarity metric, picking up out of the entire system the 25 to 100 that are the closest according to this similarity metric, okay? And then using this information to recommend some content to every user, okay? Did I forget something? Yes, and the way you recommend content, obviously, is by computing a score for each item, and you usually do this with a weighted average based on the similarity between users. Okay? So that's the way let's put it that way. That's the way you can implement a collaborative filtering algorithm. Okay? Now we're going to go into how you do this in practice, okay? Because we haven't solved everything, especially the thing that we haven't solved at this point is how we compute the scale nearest neighbors, okay?